Welcome, everyone, remote and present in person. It's good to have everyone here. And Professor Derpino is currently literally traveling as we speak. So she asked me to give a brief introduction, and I have some cheat sheet here with some notes, but I actually know the people coming in. I actually know the two students who are going to speak. Marco Misley completed his BS in electrical engineering at Università degli Studi di Genova. He graduated in December 24 and was a visiting fellow here in CAR for a period of time. We had the pleasure of working with one another on this project, and with Richard as well. We've had many conversations. And he's currently pursuing his master's degree at Politecnico di Milano, also in electrical engineering. And his expectation is that he'll graduate with his master's degree sometime in summer months. Richard Henion, on the other hand, do you have your BS?
No, I'm finishing.
You're finished.
Yes.
So he's finishing his BS in ECE, electrical and computer engineering, in about a year from now is your plan, right?
Yes.
Awesome. But he's been with CAR for quite some time now, since January of 24, and he's working as an undergraduate research assistant, Professor Derpino. My personal opinion is that the team of Marco and Richard are the most talented undergraduate research assistants I've ever come across. They're doing graduate level work. So,
Well, thank you, Mark.
now it's a pleasure to have you guys. So, Marco, you're going to start?
Going to start. Thank you so much for the introduction, Dr. Rizzoni. So today we will speak. Yeah.
Go ahead.
Yeah, so today we will speak about electrochemical impedance spectroscopy, which is a measurement techniques for battery. And so the agenda of today's seminar, we will start with an introduction of electrochemical impedance spectroscopy and application to lithium-ion batteries. Then we will discuss the experimental setup for the EIS applied to a battery cell and assessment of our uncertainties in these measurements. And last, I will explain the development of a calibrated model from experimental data and assessment of how measurement uncertainties affect the parameters estimation. So electrochemical impedance spectroscopy basically is the principle of electrochemical impedance spectroscopy is to perturb an electrochemical steady-state system with a sinusoidal excitation signal of small amplitude and frequency f. And then we measure the system response frequency and analyze this system response frequency. These techniques has several applications in electrochemistry, such for the study of electrokinetics, mass transport and diffusion, and other stuff like corrosion assessment and electrolyte characterization. So for what concerns battery, I think we can move the slides. We have basically two types of electrochemical impedance spectroscopy. We can have galvanostatic EIS or potentiostatic EIS. In galvanostatic EIS, the input signal is a sinusoidal current, and the output signal is the voltage response of the cell. Instead, in potentiostatic EIS, we have the voltage, which is the input to the system, and then the current is the output and is measured. Typically, the frequency range, we apply current or voltage at different frequencies, and we analyze the system response. The frequency range usually is from 10 millihertz up to 100 kilohertz. In this project, we use the galvanostatic EIS, so the instrument that Richard will show later applied the sinusoidal current to the lithium-ion battery, and then the voltage was measured by the instrument itself. So from the theoretical point of view, I think we can move slides. From the theoretical point of view, under this assumption, we can define a transfer function h of omega. So as we said before, the small sinusoidal input signals, and this ensures that our system is linear, as a linear behavior around the operating point. And then we want to have a time invariant system, so the system properties that doesn't change during the measurement. And in this case, a small sinusoidal current ensures the battery to have a pretty constant state of charge, state of health, and state of temperature. And so we can define a transfer function that for batteries is the impedance. So the impedance, we can see here the equation is given by the ratio from the ratio of voltage phasor and the current phasor. And so we can compute the impedance at different frequencies. And as we can see, impedance at different frequencies is a complex number given by the resistance and then the imaginary part, which is the reactance. On the right, we can see which is basically the output of EIS. So the representation of impedance over frequency, we can have basically two types of plots. One on the left, we have the Nyquist plot. So we have the real part of the impedance and the imaginary part of the impedance. Or we can have the Bode plot so that we can plot the magnitude and the phase of our cell over frequency. So basically in electrochemical impedance spectroscopy, we are just measuring the impedance over frequency of our battery. So I think, Richard, you can speak.
Thank you, Marco. So on this slide, I want to start off by trying to explain to you what the Nyquist plot, how to read that a little bit. So as Marco mentioned earlier, here's the real part of our resistance. And on the y-axis is going to be the imaginary part. You'll also notice that it's a negative value. So it's kind of flipped from what we're normally used to. That's partially to just present the information a little clearer. It's also the negative part is related to capacitance. So positive would be an inductive behavior, for example. And then some key parameters so that we can get from our analysis and data collection. So here, if this is our curve, we have high frequencies over here on the left side and lower frequencies on the right. The inductive behavior over here when it crosses the x-axis. At the moment, to the best of my understanding, we don't really know how to attribute that to a battery specifically. Often it's attributed to cables of the measurement system or maybe the geometry of the battery. Following that, we have the intercept point, and that's related to the electrolyte resistance or bulk resistance of the cell itself, kind of like pure ohmic drop. And then in the mid-range, we start to have our like capacitive behavior that's related to like charge transfer and through the electrodes and the ions moving through the SEI layer or solid electrolyte interface. So this kind of builds up on the builds up on the electrodes themselves. And finally, in the very low frequency area, we start to have our diffusion part, and that's basically the ions diffusing into the solid material of the battery. And then furthermore, we also have some how we can relate the Nyquist plot to an equivalent circuit model. So highlighted in teal is kind of R1, and that's that bulk resistance. You can see it kind of modeled down here. And then over here on the right, our R2 is our reaction resistance. And to be clear, this equivalent circuit model is kind of a basic one. So we're not really modeling here in this example the diffusion part that we mentioned earlier. Oh, okay. And then so parts that we can learn from EIS. We can get things like state of charge estimation, which we can see in plot A, how from higher state of charge down to lower, we start to see a decrease in our impedance. We can also see temperature. So colder temperatures increase our impedance, and then also aging here. So more cycles reach more impedance as well. Measurement uncertainties. So just a review or some basic definitions and why it's important. Start off, we're using small signals, so we want to be able to kind of characterize how much noise we're going to get from our measurements themselves. And accuracy for here is trueness to its real value, precision being how much we can repeat those results after repeated measurements. Then we also have our chain of uncertainties. So we have on the right, our device under test, which is the true impedance that we would have. That's not something we can actually know, but we can kind of approximate it. We also have systematic errors that we can kind of calibrate out. And then we have fixture errors kind of related to how we connect our device to ourselves. And then, and also just random noise that we can really take out. But those come from things like temperature changes or imperfect components. This is just kind of a layout of our test setup. You can see where some of our uncertainties are coming from again. This is our battery meter, and this would be like a device under testing. Also, this green wire is the something called a return cable. So we'll go into that a little bit later. Another thing that we also needed to worry about is something called four-terminal testing or sensing. So if you're not familiar with it, it's splitting the voltage and the current source and sensing the change in voltage driving current source. It's also important to note that we're using galvanostatic EIS because, let's see, if we change our voltage as our driving force, that can also lead to too high of a current through our load cells. Through our equipment setup. So this is an example of our machine. It's a Henion BT4560. It's used for measuring low impedance cells. It can give us total current voltage, impedance, temperature. The range of frequencies it can go through are 100 megahertz to about a little over a kilohertz. And it only uses galvanostatic EIS. Also, our equipment came with some specialized probes. So on the left is an older style that can incorporate a little bit of contact resistance. So we have these newer ones over here that help separate the current and voltage sensing a little more clear. There's also, I mentioned earlier, the return cable that helps reduce some of the inductive interference from the driving current through the cell itself. We also have a zero adjustment board. So this was very important to use to get repeatable measurements. You need to set this where you're going to test your device under or battery at. And you also need to make sure like things like cables and so forth are unchanging between measurements. So this was kind of important. In the graphic over here, we can kind of see how it sets a pseudo zero ohm resistance. So it's separating the sense and the source terminals. All right, and then here I have a few key parameters that we were able to set on our device. In bold are parameters that we were setting for our experimental data. And so we have a couple ranges from 3 milliohms to 100 milliohms. The max that we could read is about 120 milliohms. And then the resolution there is just at 1 micro. Also to note that we use for the lower range settings, it's a higher current. That's kind of due to since it's a lower resistance, you want to see a more of a spike with the voltage response. We also have speed settings. Those affect how many waves or periods that we use per frequency. And that's what key points there. Okay, and then here we kind of just have information on how to calculate the accuracy from the instrument itself. This is kind of a boring slide, but it does show like how we can parameterize or calculate our uncertainties there from the instrument. Next, we have our cell under test. So we have a Moly cell 18650. It's about 2.8 amp hour capacity. And its typical impedance is around 10 milliohms. So we could only measure it at 100 milliohms range for our device. Okay, and then other important part about EIS. So we needed to have a very static, stable system for our measurements. Above here is our initial cell fixture. We had it printed by one of our partners, and the key point here was to keep the cell static, the probes connected consistently, and so forth. Unfortunately, when we started collecting data, we didn't account for temperature, and we eventually realized that for us to get repeatable measurements, we needed to hold the cell temperature constant. So we incorporated a Peltier system. Peltier charge. So on this slide, we have some kind of demonstrating what happened before and after the Peltier. And blue is after, and red is before. Not important is the temperature we tested at so much as showing that we had all this fluctuation in our impedance results when we didn't control for temperature. This is a little clearer demonstration of our Peltier system. You can see where our thermal sensor is placed, where our cell under test is, where the probes are connected, our adjustment board, so forth. Okay. Then we did design two test setups. We had a test A, which was repeatability. So we basically put the cell under test and applied the probes to our cell and repeated about 10 measurements per test, and then without changing anything there. So that's to help characterize some of the random points that we should expect from our measurements. And then test B, similar, but we were detaching the probes themselves between measurement sweeps. And we did about 30 sweeps per test there. This is the outline of our procedure. So we put the fixture, the cell into the holder, set the Peltier to the desired temperature, let the cell acclimate to the set temperature. That took about an hour. Also, according to the manual for the battery tester, it recommended leaving that machine on for at least an hour as well. Then we programmed our instrument and did the zero adjustment before we took any measurements, and then carried out our desired measurement sweeps. Here we have the test A results. In blue is the individual measurements themselves, and then in red is the uncertainty added to the measurement from the manual that we showed earlier. Here's our slow result. Here's our fast result. I think it's pretty good. Also, this is data from the previous slide just presented, but this shows how little our temperature was fluctuating between measurement sweeps. So we found that was pretty good. This is just a summary table, so this isn't all the data points we collected for. And also I want to note that the red is relative, so it's not necessarily bad, it's just higher value than the green values were. And then sigma over here, that's just standard deviation. And then we also have a percentage deviation. And then how much the instrument uncertainty should be also. So I think anything below 1% standard deviation is actually pretty good. So we have pretty good results here. And then here's our test B results. So that was 30 measurements combined. And then again, in red is the instrument uncertainties. Yeah, we have pretty good results there as well. So here we have two tables comparing both test A, test B setup. Again, the color is not necessarily that, just relative. We do see that between test A and test B that we do have an increase in our standard deviation, but it's not necessarily bad. It wasn't necessarily unexpected. What is kind of interesting is how high the high frequency reactance changed percentage wise, but I think that was more correlated to contact resistance, so not necessarily a bad thing. And then lastly, we also did some variations in temperature testing. So we did about we kind of did 5-degree increments from 15 degrees to close to 40. These numbers are the measured results. And then, we had a procedure outline that was pretty similar to what we did earlier. Oh, and then also we only did 10 measurements per sweep, both at the fast and the slow settings. All right, and then here's a Nyquist plot and temperature plot for those results. You can see at 15 degrees, we have increased impedance. I think Marco mentioned that this is a good example of why, like, if your phone is cold, it just charges faster because the resistance has gone up. And also, you can see where our temperature varied pretty well. Like, it didn't vary a lot between measurements, so that's good. This is just a table summary of those results. Again, this like red is not necessarily bad. It's just, relative to the green. And where we do see a little bit higher deviation, it might be more attributed to our temperature deviation here. You see that it's a little higher this side than it is at the 50 degrees. All right, I think that's my end. I can go back to Marco.
Okay, so in this part, I will present the developed circuit for these experiments with temperature variation. And then I will explain the optimization problem that is being carried out and estimated the parameters uncertainty. So basically in lithium-ion batteries, in the literature, a lot of models have been proposed. As we can see, we can start from a very simple model, such as zero-order model on the left. And this model, for example, is very simple, and there is a very easy identification of parameters. but has for sure some drawbacks that with a model like this can be good for application like storage, or but we can do we can't appreciate the dynamics of the cell, but we can just see the steady state of the voltage response. So higher order models, such as the first order model or second order model, have been proposed in the literature and have been used. And with this model, we are able to capture multiple dynamics of the cell. And for sure, we can see, for example, the response to a step current, and we can see the voltage dynamic. But these models are used, for example, in automotive or for diagnostic. But the problem of these models with many parameters is that is hard to identify the parameters. There are higher computation, and it's also hard to give a physical interpretation to each parameter. In the EIS, there are models that are. We can move to the next slide. In EIS, as we have seen before, in those models that are all in basically in those models, we adjust resistive elements or capacitor or inductive elements. Instead, in EIS, there are different circuits and models that have been proposed that are taking into account basically two other elements that we can see: CPE, that is constant phase element, and ZW, this is Warburg impedance. And these are elements that are not commonly used in electrotechnic, but are just used in electrochemistry. And they're elements that are defined in the frequency domain, and they're used to describe the behavior of the cell in this condition. So basically, we can move to the next. So basically, the Warburg impedance represents the frequency-dependent resistance that is due to the ion diffusion in electrochemical systems. This happens especially at low frequencies. And if we see it in an Nyquist plot, it appears as a 45-degree line. The formulation of the impedance, so Warburg impedance, is depending on sigma, and then is depending on omega. So omega is the frequency at which we are analyzing this impedance, and sigma is called the Warburg coefficient, and it is the coefficient that quantifies the extent of diffusion-related impedance in an electrochemical system. So this electrochemical object is described by one parameter. Instead, we have a more complex element that is constant phase elements. And this constant phase element basically used to models the non-ideal capacitive behavior. So instead of using a capacitor, we can use this model. And this non-ideal capacitive behavior is often caused by surface roughness or inhomogeneities in the cell. As we can see here, we have the equation for the impedance in the frequency domain. And basically, this object is depending on two parameters. One is Y0, that basically is the analog of sigma and is a constant related to capacitance. And then we have another parameters, alpha, that goes from 0 to 1. If this parameter is 0, basically this element is not depending anymore on frequency, and so it's just a pure resistor. Instead, if this alpha is equal to 1, the constant phase element is an ideal capacitor. As we can see in the Warburg impedance, we have the square root of j omega. So basically, is a particular case of constant phase element with alpha equal to 0.5. We can move. Okay, so this was the model adopted. So in as I was saying before, in the literature, if we see the models proposed for EIS, there are a lot of models. Some with 5-6 parameters, others with a lot of parameters. The reasons why this model was chosen is that we have just basically 4 elements, and the CP is depending on 2 parameters, so 5 parameters at each temperature. And this was done to avoid an over-parametrization of our problem. Then, as Richard was showing before, if we were seeing the Nyquist plot of our molecule, there was just one semicircle. And basically, in the Nyquist plot, one semicircle corresponds to one RC branch. And so that's why I use just one branch of composed by Z CPE in parallel with RCT and the Warburg impedance, and this was done to represent the only one semicircle. The other two parameters in this model are R omega and RCT. R omega is the ohmic resistance, and it represents all the losses in the cell that are not related to charge transfer phenomena. And basically this resistance, with this resistance, we model the instantaneous voltage drop that we have in a cell when we apply a current step. Instead, the charge transfer resistance, RCT, it accounts for all the effects that are occurring in a cell that are associated with the charge transfer processes. So as we can see, this model basically is depending on frequency for sure, because we can compute of this model the equivalent impedance just using the basic electrotechnical rules such as series and parallels. We can move in this work. Was developed a model that was not just for one temperature, but takes also into account the temperature variation, so from T1 and T6. And so were imposed to the optimization problem two physical constraints. And I applied the Arrhenius relationship both for ohmic resistance and charge transfer resistance. And basically, the parameters that we can see in this expression are the reference resistance, the reference temperature, and the activation energy. So the reference temperature was chosen 26 Celsius degrees, and this was selected by within the range T1 T6. But basically, this was chosen between T1 and T6, but changing a little the reference temperature would not affect the problem. Then we have the activation energy, both for ohmic resistance and charge transfer resistance. This activation energy basically in a chemical reaction represents the minimum amount of energy required for a chemical reaction to occur. The other parameters that we can see in the relationship are the reference resistance, which is just the ohmic or charge transfer resistance evaluated at Tref. And then we have the RG, which is the universal gas constant. So these were the two physical constraints added to represent all the behavior of the cell. We can move. So as we can see here on the left, we have the input data of our problem that is to represent the impedance over frequency and over 6 temperatures. And so an optimization problem has been developed to fit this experimental data with the analytical model that I showed before. And in total, I have to optimize the 22 parameters. So 2 parameters each for reference for ohmic resistance and charge transfer resistance. And then we have to optimize Y0, alpha, and sigma for 6 temperatures. So 18 parameters plus 4, 22 parameters. And then I will show a statistical framework that has been adopted to calculate the uncertainty of the estimated parameter once the uncertainty of the experimental data is given. So we can start with the optimization problem. Basically, as we can see on the left, we have our experimental data evaluated at frequency Fi and temperature Tj. And with experimental data, we have also the standard deviation coming from the uncertainty of the instrumentation. We can see the real part of the impedance and the imaginary part of the impedance. Here we can see P of Tj, our vector that we want to obtain from this optimization. And the problem is that optimizing 22 parameters, we have many sets of parameters that can represent those experimental data. And so I developed this path to be sure that in the final optimization problem, the initial guess of all parameters is set properly. So as we can see, we have the real part of our model impedance. So has been just computed, just applying electrotechnical rules, and the imaginary part. As we can see, we have a cost function denominated cost function 1 that was done at each temperature Tj. So we have 6 cost function. And in the initial part, we just optimize this problem at each separate functions. This is the weighted least squares method. So we take into account when we have a low standard deviation, the weight of that element will be higher than the other, because that means that we can trust that measure more than others. So with this 6 cost function, basically we can move. Basically, with this 6 cost function using the ls-kun non-link command in MATLAB, we minimized each of this function, and we got so basically for each temperature these 5 parameters. So the parameters y0, alpha, and sigma, that they don't have a physical constraint. I didn't put a physical constraint with temperature. These 18 parameters obtained from this first optimization are used as the initial guess for the final optimization procedure. Instead, with the optimized R omega and RCT, we can go back to the Arrhenius relationship. We can change slide. We can go back to the Arrhenius relationship and no, go. Okay. No, go. Sorry. No. No, change. Go over. Okay. Go. Okay, yeah. So basically, no. Okay, yeah. Okay, so starting from the Arrhenius relationship, the Arrhenius relationship has been linearized by applying the natural logarithm, and then by substituting the value obtained from the first optimization. Basically, we have 2 cost function, both for the R omega and for RCT, such that we can basically, by minimizing these 2 linear cost function, we can obtain the value of the activation energy and the reference resistance, both for the ohmic resistance and the charge transfer resistance. So now we had before 18 parameters that were used as initial guess. Now we have the final 4 parameters, and we can set basically the final optimization to optimize the whole problem. So the final optimization basically, also this is next slide, we can go. Okay, so this is the final optimization. We have the final cost functions described by these 22 parameters. As we can see now, the summation of the cost function is done both on the frequency, so for E going from 1 to 13, so from 0.1 hertz to 1.05 kilohertz. And the summation is done also on the temperature, so to minimize the whole function. As we can see, J going from 1 to 6, so from temperature T1 to temperature T6. By minimizing with the same function in MATLAB this final cost function, we finally get our 22 parameters of the model, and so we are able to draw the impedance spectrum of the model developed at each temperature and to compare it with the experimental data. So before showing the results, we wanted to also to assess which was the effect of the uncertainty of the experimental data on parameters, because in literature we can find a lot of model of EIS, but no one explaining how, also especially the model with a lot of parameters, not explaining if I change a little the experimental data, how these parameters will change. So what I did was to compute the weighted residual vector. So it is a vector that is the difference between the real part, both for real part of the impedance and for imaginary part of the impedance, the difference between the model value and the experimental value, and this was weighted by the experimental uncertainty. Then starting from this vector, we can compute the Jacobian matrix. So basically, the Jacobian matrix is kind of sensitivity matrix of this model. And each element in position RS of this Jacobian matrix is given by the partial derivative of the Earth component of the weighted residual vector with compared to the partial derivative with respect to the to the P parameter, to the S model parameter. So we can see how the input data change if we change basically a model parameter. Then this we can move. Then basically the main assumption under this mathematical process was the measurement errors were independent, identically distributed, and normally distributed. And under this assumption, we can approximate the covariance matrix basically by this relationship. So the inverse of J transpose the Jacobian matrix times J. And then we can calculate the standard deviation of each parameter, basically doing the square root of the diagonal element in position S of this covariance matrix. So we can get basically at each temperature Tj, on the left, we can see that we can get the standard deviation of the parameter Y0, alpha, and sigma. So the parameters describing the constant phase element and the Warburg impedance. And then we can get basically the standard deviation of the activation energy and the reference resistance. I wanted also to take into account the standard deviation of temperature, because as we see before, the setup was really stable, but also there is a little standard deviation on temperature variation. And so then I also take into account the standard deviation on temperature, and through a classical error propagation, I finally calculated at each temperature the standard deviation of R omega and the RCT. So we can move. Here we can see the results. This is the Nike's plot, and this is the comparison between the analytical model impedance and the experimental data. Starting from the right, we start from the low temperature, and going to the left, we are going to the higher temperature. As we can see, there is overall a good fit, especially at the higher temperature. On the left, we have a better fit basically than on high temperature. And in this plot was also in basically the circle representing the experimental data. I also plotted the standard deviation both for real part of the impedance and the imaginary part of the impedance. Then we can see in the next plot we can see the error. Basically, I calculated the mean absolute percentage error at each temperature Tj. So was done a mean over frequency of the real part of on the difference between the real part of the experimental data and the real part of the model, and also for the imaginary part. And then so we can see with the blue line the error on the real part of the impedance that is really low for each temperature. We can see with red the mean absolute percentage error of the imaginary part of the impedance, and as we can see, this is a little higher. And then we can see with the red basically the mean of the two. So we can move the next slide. In here, we can see the optimized parameters. So the ohmic resistance, charge transfer resistance, Y0 and alpha describing the constant phase element, and sigma describing the Warburg impedance. As we can see, we can appreciate also the standard deviation of parameters in some points. In other is a little teeny, and so we can see it. But if we move to the next slide, we can see the percentage, the relative uncertainty that we got for all parameters. So as we can see, we have a really low standard deviation for the optimized parameter ohmic resistance and charge transfer resistance. And this means that we can trust these parameters more than others, and we could use these parameters for diagnostic purpose or state estimation of the cell. As we can see, the element having the greatest uncertainty is Y0. So the element related to capacitance in the constant phase element, and this tells us that this is maybe not a good parameter to estimate states or to do diagnostic or to have diagnostic information. So we can move to the observation of the results. So from the modeling results. That was not easy to see before because of the scale of the plot, but R omega exhibits an almost constant behavior with temperature, and the activation energy was really high. So really high activation energy means that we have to move a lot the temperature to have the resistance to have a variation in the resistance. And this was expected because this was in agreement with other results in literature. Instead, as we can see with the charge transfer resistance, the activation energy is much lower. So we had that the charge transfer resistance was varying a lot with basically with temperature, and that's why we see a really different Nyquist plot varying the temperature. And also this result was in agreement with other papers. So the adopted circuit with the two Arrhenius type physical laws provides a meaningful description of the experiment, as we were seeing that there was a good fit, and also the standard deviation of parameters was acceptable. The problem with that I experienced with this model, and that is common, I think, for a lot of EIS models, is that having a big number of parameters, when we strongly reduce the standard deviation on experimental data as input, the Jacobian matrix that has been used to compute then the covariance matrix and the standard deviation of parameters approach to a singular condition. And this is a problem because it reveals that we are over-parameterizing our problem, and there are some possible correlations among parameters. The problem is that elements such as constant phase element and Warburg impedance, also the physical meaning is not still clear, and so it's not easy to understand really what's going on. Then the last consideration about modeling is that is crucial to establish a good trade-off between the model accuracy and the number of parameters to have a robust parameter estimation. Instead, for the experimental part, the observation for the experimental part, basically, we found that under certain conditions, so with a very good stable setup, the Aoki BT4560 was found to be capable of making reliable and repeatable measurements. And what was interesting that we didn't find so much in the literature, that the small changes, as we were seeing before, also alpha Celsius degree in, for example, in the room temperature, can greatly change the impedance measurements. And so that's why we had to use the PLTSL to do a proper assessment of the uncertainty. So I think we're finished. Thank you for the attention.
Thank you, everyone. Do you have any questions?
Please, time for questions.
I don't know if the online is able to ask questions directly.
Sure, if you can manage that, they can put it in the chat or just speak up. I don't know if they're enabled to speak, but.
Okay, yeah, just put it in the chat if we don't hear you. That'd be great.
First of all, I congratulations for presentations. Really nice work. I see how interesting and relevant the topic is, especially in terms of say diagnostic. So you can use this tool to estimate the state of health, the temperatures, the charge, which is still a unresolved issue in today's batteries.
Yeah.
Well, I have a couple of questions, and the first one is on slide 30. Yeah. And so here, maybe I didn't get it. What are we looking at? What are we comparing in these two plots?
So left side was the slow speed setting, so longer measurement time, just more. Let's say we have 1,000 hertz that we're measuring at, which is does 128 samples at that frequency, and then at the fast it does like 8. So it's kind of comparing that the slow is a little bit more precise, more accurate than the fast is.
So
But go ahead.
like, is it is it your point? Oh, the fast, doing it fast is just as good as the slow? Because you said multiple times, it's pretty good results, but I didn't understand what you mean by.
I would say, at least with this cell, the fast was good. But it probably is acceptable for most applications. If we wanted a very deep characterization, maybe the cell would be the.
Maybe it's not clear to me, but what do you mean by it's acceptable? Like, the plots are very similar,
Yes.
and I assume it's the same cell?
Yes, same cell, same state of charge.
Perfect.
I don't think, as we tried to control as much as we could to keep variation between those.
But so the only difference is that you have a slightly larger error.
Yes.
Is this correct?
Yes,
So the two methods are almost equivalent.
yes, in this scenario, yes.
Okay.
Yeah.
So like the point here, like what you want to pass with this is that doing it fast is almost the same as doing it slow.
Yeah.
So you
Yeah.
can reduce the number of like time.
Right.
Like-
I would
What's the
I would say for characterization, like if you wanted to say this is what we expect our impedance to look like, I would do a very slow characterization, and then hey, we just took this cell and to see where it's at. I think we can do fast.
okay? So like in terms of, let's say you want to develop a standardized test
Hmm.
to check aging. The
Yes.
first time you do it very slow,
Yeah.
and then you can run the test more frequently with a fast characterization and check where the point is.
Yes.
Okay.
Yeah.
Okay. Interesting.
Yeah, thank you.
Thanks.
And then something else I think you mentioned, and I don't know if we emphasized this, unfortunately, for diagnostic purposes, another advantage, it's non-destructive. So when you take measurements on the cell, you don't destroy it. Now, changing the state of charge, I mean, you're going to,
You do it.
yeah, but that's trade-off, right?
Yes. But that's gonna happen anyway, right? If you use the battery.
Yeah, exactly, yeah.
Just, I think the only difference is that here you have to use small impulses, right?
Right, yeah. Yeah, for linearization.
Yes. I mean, I have another question. If you-
Why not?
So this is more like a comment for Marco online. I don't know if you can hear me.
Marco, can you
Yeah.
hear the?
Yeah,
Okay.
I can hear you.
Yes. So, okay, my question is about the optimization procedure, and how come did you? So, like by looking at the Nyquist plot that of slide 51 or 50, something like this. Yes, this one, 48. You can see that they are pretty much like the curves are can be obtained via an affine transformation of one another, and also from when you plot the values of the coefficients, you can see that the trend is pretty much linear. So why did you choose to optimize well, a set of parameters for each temperature as opposed to optimizing only a set for a given temperature and then including two, I guess, parameters for the affine transformation?
Yes. I don't know the answer honestly, but I mean that was the I think for me the easiest procedure, but for sure optimizing before and then applying. That was interesting to understand because the shapes is always repeated, and so I think that we can get basically one Nike's plot from the other and vice versa. And so that could be tried, but I just did that because I think that was, at least for me, just studying this topic and optimization problem, that was the most easier way to get the result.
Yeah, I mean, I understand you first try it out and see what the curve looks like, and then maybe you, as a future step, you can transform. You can use a transformation to fit all of them. But just as a maybe future remark, maybe it's interesting for follow-ups with the research. I think some of the problems that you that you showed in the last slide maybe could be solved with a multicollinearity analysis to check if one of the parameters is actually dependent on others, and to balance maybe the number of variables in the model and keep them as low as possible. You could use some metrics as AAIC or BIC, which are tools to compare different models and give you the one that with the most likelihood fits better with the lowest number of parameters. But this is just for future reference.
Good ideas for continuing this work.
Just
Guys, well done. Very nice. Thank you. Nice.
Thank you so much.
So, ciao Marco.